We have arrived at the beginning of the last chapter, chapter 19, and then this course here is bye-bye. So chapter 19 is called electrochemistry, and it deals with electron flow. Well, electron flow is connected to electrical energy, and electrical energy is extremely important, right? We run most of our appliances and things in our house with electrical energy. Right here we have an electric car, and the batteries are shown here. So there's energy storage is very important, and that's one of our biggest problems right now is energy storage. We need to make it more efficient. We need to make it available, because when you use solar or coal or any kind of generator, once you generate this electricity, it needs to be used up. And so if it goes to your home and you don't turn your light bulb on, that you may not be charged for that energy, but that energy has to go somewhere. And if it doesn't get used up and we don't store it somewhere, it's lost. And so this is one of the biggest problems we have. And electrochemistry is the foundation to solve this problem, right? So if we can generate, like, it's simple. During the day, the sun shines. We can have all the solar panels available to us running and generating this electricity, but at night we don't have it. So we need to be able to store that. And so we've already been exposed to electrochemistry. In the first semester, we called it redox chemistry. Redox chemistry deals with reactions that transfer electrons, right? And the foundation is in bonding. If you go all the way back to bonding and you look at the periodic table and you select any of these metals, for example, right, like sodium, which is in group 1, you know that sodium is very reactive. It's a solid, and that's because it wants to get rid of its electron, right? It has one electron, and if you remove it, it becomes noble gas-like. That's the driving force of ionic bonding. So we know very well that sodium will react to become charged, and when it becomes charged, it loses that electron, and then that would be called an oxidation reaction. Okay, but you can't just have an oxidation reaction, you also have to have a redox reaction. Why? Because, not a redox, a reduction reaction. Because this electron isn't going to hang around. It has to be mopped up somewhere, right? So, and if we look at a nonmetal like chlorine, we know chlorine needs an electron. So it's ideal for chlorine to be reduced with one electron to become chloride. And so that foundation, we don't think about it that way when we talk about bonding, but that's what it is. It's a redox reaction. Let's take a look at an example of a redox reaction. There's one shown here, and I just told you that it's about transfer of electrons, but we can't really see the electrons. They're just not shown. So we usually pick them apart into half reactions that shows the oxidation and the reduction. That's what I want to review with you at this point. So the step number 1 is for us to assign an oxidation number to all of the elements that are present in this reaction here, right? And so those are called oxidation numbers, and they're not always the same as a charge. Now in the example here shown, zinc is by itself, it's just a metal, so it hasn't lost any electrons yet. It has an oxidation number of 0, which happens to be the charge as well. And the copper here, we know nitrate's negatively 1 charge, so copper has to be +2, so its oxidation number is +2. And we can also do this for nitrogen and oxygen, but I'm going to leave that alone for now. We'll revisit that. Just note that we know the overall charge of the nitrate, and it doesn't change, so we know there are no electrons being transferred to the nitrogen or the oxygen. But we can also assign an oxidation number to nitrogen and oxygen, but we know nitrate is a covalent compound, so there aren't charges. So we call those oxidation numbers. So if you assign an oxidation number to a nonmetal that's part of a covalent compound, then those are called oxidation numbers. In fact, they should always be called oxidation numbers. They just are not. They are sometimes also charges in the case of metals or monoatomic anions like chloride, sodium chloride, right? Okay, so then the oxidation numbers on the product side. Now zinc has a +2 charge, and copper has a 0 charge. And now we know that the zinc is transferring electrons to copper, so zinc is being oxidized, it's losing the electrons, copper is being reduced. In fact, copper helps oxidize the zinc. It's a stronger oxidizing agent. Maybe you remember that as well from our discussion in chapter 1. But we can single out the oxidation. We can just write zinc goes from 0 to zinc 2 plus, and in the process loses 2 electrons. And if your electrons are being produced, if your electrons are on the reactant side, then that is the oxidation half reaction, oxidation here. If we do the same thing for the copper, copper goes from copper 2 plus, it takes up 2 electrons, so the electrons are written on the left. And oops, this is copper Cu solid, and that now has a 0 oxidation state, and that is the reduction. So by writing the half reactions here, we can nicely see where the electrons are coming from, which element is reduced, which element is oxidized. And so if you put this together, this is the nitrate ion is out there hanging out going, hey guys, can I be involved? And zinc and copper are like, you are not invited to this party, buddy. Stay where you are. And that's the spectator ion, right? He stays outside the party. And so if you bring it all down together, we have zinc and copper. So here we're just focusing on the actual chemistry, right? We would call this the net ionic equation if you wish. That goes to zinc plus 2 and then copper solid. So this is the redox reaction, and so the electrons fall out, right? They're no longer part. They are part of the reaction. We just don't see them. They're kind of like spectator ions, except they're not, right? I suppose you could refer to the electrons as the liquor you're sneaking into the party, especially if you're underage. All right, so this is just what I have written up here. This is, let's call this the net ionic. So how do we sign oxidation numbers? A few things we know already, but how do we do it for nonmetals? Like, what about carbon dioxide? Do they have oxidation numbers? Carbon does and oxygen does. How do we figure this out? First of all, elements are by themselves, like zinc and copper as a solid, right? They always are 0. Also elements, the diatomics, when they're bound to themselves, like hydrogen, chlorine, iodine, nitrogen, any of those diatomics also have an oxidation number of 0. And I should put oxygen in this bunch. If it's O2, it's going to be 0. Monatomic ions, charge on the ion, right? So like zinc, chloride. And so that applies also if we have calcium chloride, AQ. These are monatomic ions. They are chloride ions and calcium ions. We write them together, but if it's aqueous, that means we have calcium ions and chloride ions, right? So those have the charge of the ion, -1 for chlorine, +2 for calcium. Oxygen is always, when not with itself, right? It is always -2. Unfortunately, we have an exception, but those are rare, and we probably won't have to deal with them much in peroxides. There are different kinds of peroxides. The one you're familiar with is hydrogen peroxide, and I'll come back to that. How do you recognize it? Hopefully by the name. If not, we can use rule number 4 to determine that, because rule number 4 says that hydrogen is always +1, except for when it is bound to itself in its diatomic form. It's always +1, except -1 in binary compounds. Now this is a binary compound, but with metals. Okay, so if hydrogen is bound to a metal, and I'm running out of space here, but there's a compound called calcium hydride, for example. It's not that difficult to realize that calcium is either 0 or positively charged, and so in this case it has to be +2, which means this is one of those exceptions where hydrogen is a hydride, so this is a binary compound bound to a metal, and that's the key. Hydrogen and oxygen are both nonmetals, so if hydrogen is +1 here, that means oxygen has to be -1, so this is a peroxide. But for the most part, we don't have to deal with peroxides, so knowing that oxygen is -2 in most compounds and hydrogen is +1 is probably a good thing to remember. Rule 5 is not all that important, because if you have something like fluoride or chloride, it's usually bound to another metal, and we can determine that. So the halogens actually have a whole array of different charges, but the really important one is number 6. It's the sum is 0 in compounds, and the sum of polyatomic ions. I didn't realize I had a typo here, but must fix later. So the sum is 0 in compounds, or equal to the polyatomic ion charge, right? So if we have nitrate, for example, the charge of nitrogen plus the charge of oxygen times 3 needs to equal -1, whereas here for hydrogen peroxide, the charge of oxygen, all of the oxygens plus the charge of all of the hydrogens has to equal 0 here, because this is a neutral compound. All right, let's practice that briefly here. So here we have perchlorate, ClO4. It's not a peroxide, so oxygen is -2. If we have 4 of them, that would be 4 times -2, which is an overall -8 charge. And so the charge of that single chlorine has to be plus -8, has to equal -1, so it has to be +7. So here chlorine is +7, which is pretty high. Let me revisit this real quick. Okay, so halogens, all right. Fluorine is always -1, others are -1 except when combined with oxygen. Okay, so this is here, right? So here we have halogens with oxygen. So they can be those are really strong oxidizing agents, and all of those. One of those is hypochlorite, ClO-, which is sodium hypochlorite, which is bleach, right? So we know bleach is a strong oxidizer, and it makes sense because in this case chlorine has a +1 charge. We know chlorine is more likely to be minus, so it's going to want to take up electrons. It wants to be reduced, right? So its driving force is, and I'm talking about just that positively charged chlorine. Think about +7, geez, right? It wants to go to -1, so it's going to take electrons from elements that are around it, that they're exposed to, right? You pour bleach on algae, that chlorine is going to want to destroy that algae, right? And so this is how the cleaning power, some of the cleaning power of bleach, for example, works. It's a strong oxidizer, right? And so here it's +5, right? It's the same idea. Oxygen is -2, we have 3, and so +5 plus 3 times -2 would equal its overall charge. This is chlorate. N2, element by itself, 0. Here's a monatomic ion, oxygen, so it's just -2. Let's take a look at CH4. Carbon is not a metal, so hydrogen is going to be +1, which makes carbon +4, because 4 times +1 +4, -4, because 4 times +1 -4 equals 0. Otherwise, if carbon was +4 and hydrogen was +4, the charge of CH4 would be +8, and we know it is 0, so I made a mistake. Okay, ammonium, same idea. 4 hydrogens, each of them positively charged. But the nitrogen here is only +3, not +4, because we have to have an overall charge here. Wow, I did that again. It's -3, of course. -3. Sulfate, +6, right? Because we have -8 and +6 -8 equals -2. carbon dioxide. Now here, and this is interesting because we can burn methane with oxygen. And so here we have carbon. See, I was right, it's +4. It's a stone there. If oxygen is -2, then this is -4, and the carbon here has to be +4. So this oxidation here from carbon and methane to carbon and carbon dioxide is a transfer of 8 electrons, right? So, and just as a final reminder, those are oxidation numbers. They are not charges for these covalent compounds. All right, so let's take a look at another one. Just to drive the point across, the first thing you want to do is you want to identify or indicate the oxidation numbers of all the elements involved in a redox reaction. So sodium here by itself, element by itself, chlorine, element by itself, and over there they are forming sodium chloride as we expect. So this is +1. And this is -1. Now we can pick it apart and write the half reactions. We know that sodium will go to sodium plus and 1 electron. That is the oxidation. Right? Oxidation, the loss of electrons are, this is the elements, atoms are being oxidized and gaining the electrons. Chlorine gains it. See here we have Cl2, so we have 2. I could have done that here. We have 2 and 2, then we need 2 electrons. You know, the electrons also have to balance in these reactions. So here we have chlorine gas, or chlorine as an element, and 2 electrons, 1 go to each chlorine, will then produce 2 chloride ions, and that is the reduction. Okay, so those are the half reactions here. When we come back, we are going to look at, what are we looking at? More half reactions. Yay!